So without further ado, I'm going to introduce Waleed Abdalati, who is, of course, not just a professor of geography, also the director of CERES, the Cooperative Institute for Research in Environmental Sciences, and an alumnus of the department. So really fitting for him to speak to us first.
All right, thank you. All right, so I'm Waleed Abdalati, and as Emily said, I am an alumnus of the department. I sort of tell you, it was sort of a strange path to getting to that point, but I grew up in upstate New York, and my dad died when I was 12. Don't worry, the story gets better. I don't want to start with that. But we had no money. That's the point. No money. And so I was hell-bent on finding a job that was, majoring in something in college that was employable, right? I was going to be an engineer. I was going to get a good salary and get on with my life. And so I worked hard. I got my degree in engineering. I did well in school. I had a few jobs lined up. And at 22 years old, I was better compensated than most of my colleagues. And I was terrible at it. And I hated it. I would get to work late, I would take long lunches, and I would leave early. And that's not who I was, right? I couldn't reconcile how hard I had worked to get to that point with how little I was working when I reached that point. And I'll tell you, when I was done with undergrad, I was done, right? I was tired of being poor. I was going to go out in the world and get some money, get a car, eat, something that wasn't Wonder Bread and Twinkies. And I never thought I would go back to school. But when I realized, why am I not happy? Why am I not performing well? I remembered something that, ironically, I learned in my human sexuality elective when I was an undergraduate student. This is great, and I'm sorry to take this much time, but it's worth understanding how people get to where they are. So this professor, you can imagine I was an engineering student, so human sexuality was the course. We all took it. And he did something wonderful. It was one of those huge classes. And the first day, he handed out index cards to everybody. He said, I would like everybody to write down one question about sex that you're too embarrassed to ask your friends. You don't want them knowing you don't know. And they were typical stuff. Can you get pregnant standing up, or stuff like that. Maybe that's not typical, but somebody asked that. You can see why the anonymity of the index cards was appealing. And he would do it, answered 3 questions every class, and one of them was, how do you know you're in love? It was a beautiful question for a class like that. And he paused and he said, it's pretty simple. If it energizes you, you're in love. If it drains you, you just think you're in love. And you think about that, since there are no undergrads here, I'll say it, but you remember, oh, but I love her. This is killing me. I love her so much. We've all, don't want to admit it, but we did it. So I thought about that, and I thought, the thing is, the work drains me. It's not right. I'm not in love with what I do. So I decided, shocked myself, but decided to go to graduate school. Again, in engineering. I didn't quite get the point right off the bat. I thought maybe if I learn more, I'll like it more. But when I was in my master's program, I took a class in geography, and it was a boundary layer climatology class, and there was some remote sensing, looking at the Earth from space. And I thought, wow, this is really fascinating. And I went to talk to the professor, Connie Steffen, some of you may know or remember. And I said, I want to do this. I want to work on this. And he gave me some projects to do. He said, if you do well, maybe you can be a graduate student. I'll take you on as a graduate student. And something amazing happened to me. I woke up one morning dying to get to that little student office and finish what I didn't finish the day before. And I thought, wow, this is what it feels like. I'm energized. And I haven't looked back. And it's given me, so I got my PhD in the geography department here, and it's given me tremendous opportunities. And I'm just going to walk you through a few of them. I started as a research scientist at NASA Goddard Space Flight Center. I did a lot of work in the field. the Greenland ice sheet, and you know, that was the work wardrobe at the time. And then I ended up, after 12 years at NASA, I came back to CU. I had the opportunity to join the department, to join Ceres and be a professor. And NASA called me back. I did a 2-year stint in NASA in Washington, D.C. as the NASA chief scientist. And that was my official NASA photo. And I want you to contrast that with this. And my wife looked at it and she said, God, you look like you're clenching. You look like you're just, you know, you hate sitting for that photo. And this was the good one. You should have seen the ones they took when I left, because 2 years in Washington really wore me down. I came back here to be the director of Ceres. This is actually the largest research institute on campus. We bring in, this year was a little less, but about a fifth of the university's research budget. And just as a little aside, one of the projects I've been involved in was a 4-part television series for PBS on citizen science that I hosted. So a tremendous, you know, if you had asked me, I never would have guessed any of this could have happened. But it's the power of a good foundation, which I got here. And it's the power of really loving what you do. And what I love about being a professor is I see the enthusiastic students. I see the ones that are saying, yeah, this is what I like. This energizes me. And I can't help but think of the successes that they'll realize or experience. And it really thrills me. It makes me very happy. So unlike this guy, I get a lot of energy being here. I lost a lot of energy. I love that picture because the lights are going. It's just busy. DC is busy. DC carries a lot of overhead. Life there just has a lot of overhead. So it's a little bit about my background and some of my experiences. What I want to talk about today is the power of perspective. What I do is I look at the Earth, primarily the ice, from space. And if you go back to the earliest humans, there was always some value of being high, of being able to survey the landscape, have the larger perspective, whether it's looking for food or whether it's being able to assess threats before they reach you. The power of this view, of this distant view, and seeing things in a broader context really, really shapes the way we live, really informs the way we live. So this is something that has been sought after for many, many, many years. This is the first, oh, I didn't get the laser pointer out, but this is the first aerial photograph ever taken in 1860 by the great Nadar. The name is up there, I won't try and pronounce it. Patented the idea of using aerial photographs for map making and surveying. It took 3 years, but he finally got himself in his balloon with a camera and managed to take this photo of Boston. And even that, you can imagine, if you've never seen your neighborhood from altitude, this is a transformational image. And we have similar ones Earth-wide. So this is a balloon at 2,000 feet altitude. The quest for going into space was really full bore since we could first launch rockets. We put cameras on them. So this is the Earth from 65 miles altitude, 101 miles altitude. Better camera on this one. Apparently between 1946 and 1947, photography really took off. And then Sputnik happened. The Russians launched Sputnik. And it was just a satellite, just orbited the Earth, and it just beeped. And that beep was referred to as the sound that forevermore separates the old from the new. Mastering space was a very, very transformational moment. And it threw shockwaves through American culture because the Russians did it. You know, space was viewed as the mark of superiority, right? If you could conquer space, you could conquer the world. So the U.S. in earnest tried to catch up with the Russians and meet that challenge. I'm going to take you back in time to the early 60s, and this is what television was like, kids. You hearing it? Okay. Tyros, 1960, new era in satellite meteorology. Gets better.
The historic launching of the Thor Able carrying the Tyros 1 in its bulbous nose takes place at 6:40 a.m. A peacetime use of a deadly war missile that promises humanity a new era in meteorology. Graphic animation supplied by the National Aeronautics and Space Administration shows how the last stage of the rocket shot the satellite into orbit. A circular path over the Earth, 50 degrees north to 50 degrees south, between 400 and 450 miles out in space. A flying lady's hat box that circles the Earth in 90 minutes, during which every 2 seconds, the wide-angle lens scans 800 square miles. Recordings it's directed to send back to this receiving station at Fort Monmouth, New Jersey. Another space triumph for the U.S., which is explained to Ike at the White House by Space Agency head Glennon, who produces a picture sequence of the satellite scanning.
The president looks thrilled. So anyone nostalgic for the 60s, you're not missing much. I loved some of the terminology. You all picked up on that. The graphic animation. My figures are going to be a little nicer than this for the rest of the talk. But this is an important thing. This is what we thought the world looked like. There's some rivers, there's land, there's some lakes, some clouds. They probably look like this. We didn't know, right? So this was really a powerful transformation in 1960 about how we look at and understand our world. And this was born of the space race. This was born out of a desire to primarily to beat the Russians in space. And that culminated with the landing on the moon. And I'll tell you one more story, and then I'll stop with the stories. And forgive me if you've heard this, but when I was a kid, I was just like every other kid. I wanted to be an astronaut. I just assumed I was going to go to the moon one day, because that's what kids did. And my best friend Matt Perry and I, we would pretend we were astronauts on Apollo 11. We were going to go to the moon. And Matt and I would go in his kitchen, we'd drink Tang, because that's what the astronauts drank. We'd get football helmets, and we'd walk really slowly, like we saw on TV, across his yard, point into the crowd, and go into his shed and shut the door and do a countdown. And we'd throw ourselves against the side of the shed as we're hurtling through space, right? We'd land on the moon in Matt Perry's backyard. And it was Matt's yard, Matt's shed, Matt's Tang. So Matt was always Neil Armstrong. And I got to be Buzz Aldrin, so I'd let Matt go, have his fun, and then I'd go join him. And this is true, kids are mean. Sometimes there was a third kid, Scott, I won't share his last name, who wanted to play with us. And we'd let him be Michael Collins, the third guy, and we wouldn't let him out of the shed. He just had to sit there and listen to us having fun. So, space stimulated a lot of interest in science and technology in kids my age. But through that, NASA revealed something incredibly, incredibly powerful, and that's the perspective on Earth. Okay? The pale blue dot, this sitting suspended, not literally, but sitting in space, alone. And I love this quote by Bill Anders. We came all this way to explore the moon, and the most important thing we discovered was Earth, from this Earthrise photo. Incidentally, Life magazine named this the most influential photograph of all time. It's easy to take a good photograph when you got the nation's space program behind you, but it's still very, very powerful. And there is a quote that I love. Man must rise above the earth to the top of the atmosphere and beyond, for only thus will he fully understand the world in which he lives. Okay, this was said by Socrates in 400 BC. So forgive all the man and the he and all that. That's just how they talked back then. But it was understood, the power of perspective. And scientists, engineers, nations have sought this, have used it ever since it became available to us. And things really got going in the 60s. The Nimbus series of satellites, Nimbus is Latin for clouds, was established to measure various phenomena in the atmosphere and on the surface. Of particular note, the total ozone mapping system, the coastal zone color scanner looked at Earth's ocean colors, Earth radiation budget looked at the radiation leaving and entering the Earth, and there are a few others. I'll talk about the microwave sounder in a little bit. But to explore the Earth. And from that, we were able to look at hurricanes like we never had before. We could see the eye of the hurricane. We could see the swirl, the motion of the hurricanes, the movement of the hurricanes through the Gulf or out in the Atlantic. I mentioned the ozone instrument simply by leaving the planet and looking back and measuring the ozone. We saw the evolution of the ozone hole. The black is no data, but you could see the ozone hole over Antarctica forming, becoming more and more intense. You can see the low ozone levels here, which block harmful radiation. Actually, the incidence of cancer in the decade of the 90s was 400% greater in New Zealand than it was the rest of the world. This is simply the absence of the ozone hole. Led to important policy decisions, the Montreal Protocol, banning the ozone-destroying chlorofluorocarbons in sprays. The power of perspective. When we look this way, we see things we otherwise couldn't. This shows the life on the planet. So in the case of land, we're looking at essentially a proxy for vegetation health. And in the ocean, we're looking at a proxy for ocean primary productivity. How much phytoplankton is in the ocean? And that has implications for the planet in terms of carbon uptake. Phytoplankton and vegetation take up carbon dioxide, respire oxygen. And in the case of the primary productivity, this is the fundamental element of the marine food chain. So the health of the fish and marine populations depends on the health of the primary productivity. From space, by looking at certain channels on these satellites, certain slices of the visible spectrum of energy, we could assess this. I'll talk a little more about Arctic and Antarctic sea ice cover, but by measuring the way microwave energy, so we can't see this, okay, but we can build instruments that can detect the emitted microwave energy at different wavelengths. Okay? We could track the amount of ice cover, the concentration of ice, which is what you see in the bar on the right, from these multi-channel sensors, because ice emits energy differently than water does. I'll leave it at that. It's much more complex than that, and we actually have one of the world's experts, Mark Serez, in the back, who can tell you all you want to know about that. The Landsat series. So Landsat is basically I'm selling it short if I call it a sophisticated camera, but it makes measurements, again, in certain parts of the electromagnetic spectrum. Measures green energy, measures red energy, measures near-infrared energy that our eyes can't see, but that vegetation in particular reflects very strongly. Plants look green because they reflect green light. We all learned that in science class in 6th grade. Well, actually, I think I missed that day, but I learned it somewhere along the way. If your eyes could see near-infrared, plants wouldn't be green, they'd be near-infrared. And so we detect land. We can map geological features by measuring in these wavelengths. But in the case of vegetation, these data, so you can see from the 70s almost continuously through what we hope will be beyond 2030, we can see a tracking of the land characteristics with Landsat. And just one result is the greening of the Arctic. As the climate has warmed, the Arctic has warmed, it has gotten greener. Vegetation has thrived. With climate change, there are winners and there are losers. Plants in the Arctic are winners. I won't talk about the losers. So these are a few satellites, and what we have in orbit now is an Earth observing system that's a number of sensors that look at land, look at water, look at rivers and lakes as opposed to waters in the ocean, that look at temperature, that look at radiation, that look at energy characteristics, look at health of ecosystems, look at atmospheric chemistry, all kinds of phenomena that we can view from space that allow us to put these together and tell a story about how our Earth is changing, where it's changing, and why. And the most dramatically changing place on Earth, from my perspective anyways, is the Arctic. What you're looking at is the Arctic sea ice cover, and you see that it's shrinking as we approach the summer and late summer, early fall, and then it starts to grow again in the winter. And this is overlaid on land. You can see the vegetation in green, the snow and glaciers and ice caps in the Canadian Arctic, for example. The Canadian Arctic, for example, leaving you here in Greenland, which is where that picture was up there that you saw of my tents and my cigar. It tells a story, and we spend a lot of time and energy unwrapping that story because it's an important story. It's the story of our planet. It's the story of how we live. And so in the case of Arctic sea ice, these are sampling of instruments that help us understand various properties. How it's moving, how thick it is, the amount of ice, its extent, how reflective it is. Ice is white. Ice reflects a lot of sunlight. Ice insulates the ocean heat. So it affects the Earth's energy balance by controlling the reflection of sunlight, and it affects, well, energy balance and climate and weather phenomena by trapping the heat in the ocean. So as it starts to disappear and this moisture and energy is released to the atmosphere, this is a major perturbation of the climate system. So this is why we track, one of the reasons why we track the health of the Arctic sea ice cover. And one index is the sea ice minimum. It's not the only one, but the ice grows in winter, shrinks in summer, grows in winter, shrinks in summer. And when it shrinks at its smallest point, that's when the most energy is available to leave the Arctic Ocean into the atmosphere. That's where, significant impacts and implications for our climate lie. So there's a strong interest in tracking the sea ice minimum. And this is something the National Snow and Ice Data Center, again, Mark Serez is the director of that, another alumnus of this department, is tasked with watching, handles a lot of media. The world watches this. What is the ice doing? One of the reasons is human civilization has not known an ice-free Arctic. This is a major perturbation of the climate system, and we are well on our way to a seasonally ice-free Arctic in the summertime. Now, there are good implications of that, economic, where as shipping lanes open, we can traverse the Northwest Passage, and goods can get from Asia to Europe without having to go the long way through the Panama Canal. But there are issues associated. We don't know the implications for climate. I'll tell you who's paying the most attention to this is the military, the Navy. We have an exposed border. We have competition for resources. There is a strategic reason to be paying attention to this, not just climate scientists, but this has economic implications, this has implications for national security, this has implications for science, for weather, for commerce. So one of the tools, that was just the extent, but another one of the tools is age. You know, when ice freezes, if it lasts a few years, every year it continues to lose a little more salt. Okay? And that change in salt, so sea ice, the frozen veneer of ice above the Arctic Ocean, is fresher than ocean water, because when it freezes, it loses brine, it loses salt. And the older it is, the fresher it is. It loses more salt over time. And the salt in the ice affects the way it emits microwave energy. So there are algorithms by which we can track the age of the ice. Okay? And this is showing, you probably can't see it, but the bar all the way to the right is more than 4 years old. The bar to the left is 0 to 1 year old. So we track not just the extent of the ice, but the age of the ice. So this is 1984, September 1984, where the ice, the minimum sea ice extent month is September, and this is 2016. And you can see, if you look at the histogram, you can see the old ice disappearing and the young ice taking up that space. So the thick, hardy stuff that's been around a while is going away, the ice is shrinking, and it's getting younger. We also can measure thickness. This may be a bit of a confusing figure, but we fly a satellite along that fires, in this case, actually this is lasers, fires laser pulses. We know the speed of light. We know the position of the satellite. We measure the time it takes the laser to hit the surface and come back, and we can estimate the height of that surface. And as the instrument flies over ice versus open water, you get a baseline of the height of the open water, and you get the height of the ice. And roughly the ice is 9/10 the density of the water, so 1/10 of the ice is above the water, so you take that thing, that number, multiply by 10, and you get the ice thickness. Alright, so we're able to track the changes in ice cover, and this is the changes in ice thickness over time from two different instruments, one a LiDAR, one a radar, and we're seeing a decline in thickness. So we're seeing a change in extent, we're seeing a decline in thickness, and we're seeing a change in the ice age. Now normally, younger and thinner, which is what the ice is doing, is a good thing, right? We all think, oh, if I were younger and thinner, what would I do? I know what I would do if I were younger and thinner. But if you look at it, in the case of sea ice, it's not a good thing. You don't want younger and thinner in your sea ice. You may want it in your husband. I'll tell my wife, showing her these pictures, my wife. But so this is a real perturbation. I'll let you just gaze on this for a while. This is a real perturbation. That should have been my NASA photo. I would have kept the job if that were a real perturbation to the climate system. But the beauty is, it's not enough to watch. Just watch it shrink. That's instructive. But it's when we combine that information with other information, like the ocean temperatures, like the wind, that we can start to understand, is the ice being advected away? Is it just being carried to lower latitudes? Or do we have, as you see in red here, the intrusion of warm waters that is melting it from underneath, or the intrusion of warm air temperatures that's melting it from above? We got a lot of smart people, Mark being one of them, me not being one of them, that are working on this problem and trying to understand not just why, not just how much it's disappearing, why it is, and what are the implications? That's the bigger question of the shrinking Arctic ice cover. All of this is because of the space-based perspective. My own area of research is on ice sheets and glaciers, the Greenland ice sheet and the Canadian ice cap, so I've spent a lot of time in an airplane over a lot of these places in the Canadian Arctic, and a lot of time on the surface and in aircraft over the Greenland ice sheet, trying to answer one basic question, which is, how much are these things contributing to sea level rise? So this is a figure showing the areas impacted by a 1 meter sea level rise. I can't even get my head around the 2.2 million square kilometers. I don't know what that means, but I like the picture. I think it conveys it well. But 145 million people at a cost to the U.S. alone, a global cost of $944 billion. It's very easy to see where the first meter of sea level rise comes from, and it may well be in our future this century. So understanding how much the ice is changing, because the implications depend on how fast the oceans rise. If it rises a meter in 500 years, that's a lot different than if it rises a meter in 10 years. Right? So, you know, a meter by the end of the century is certainly a reasonable estimate. It's a little on the high side, but these are the places that would be adversely affected, including Washington, D.C., and all of the politicians' favorite vacationing spots on the eastern seaboard. So we try and figure out how and why the ice sheets are changing and how will they change in the future. Again, with the satellites and the aircraft, we're able to do that. These are the tools that help us understand how much it's melting, helps us understand how much it's growing or shrinking, helps us understand the spatial extent, the reflective characteristics. And the instruments that I work with and my colleagues are airborne altimetry, and I just described it for spacecraft, but again, a plane flies, you fire a laser, you measure the travel time, and by knowing the position and the travel time, you get the height of the surface below. You repeat that, year after year, or you let 5 years go by and you go back and do it again, and you can measure the change in height. Where is it shrinking? Where is it growing? Another instrument is the Gravity Recovery and Climate Experiment. This is one of the coolest instruments I know of for space-based observations. It's 2 satellites. They're about 100 kilometers apart, and there's a little radar right now. The next version will have a laser that measures the difference between the satellites. And when a satellite orbits the Earth, what it wants to do is just leave, right? If my computer's the Earth, it just wants to leave. But the gravity of the Earth pulls it down. And this is how orbits happen. Instead of leaving, it just remains in orbit. And the more gravity, the faster the satellite moves. So GRACE is 2 satellites where one flies behind the other. And imagine this is Antarctica, or the Greenland ice sheet. As the first satellite approaches and hits this high gravity area, it accelerates. Okay? It picks up speed, so the separation between the satellites increases. And then the second one accelerates as it catches up, and this one slows down as it's passed over the ice sheet. So by measuring the separation that occurs over the ice sheet, we can say something about the mass beneath it. I use the ice sheet example, so the more it separates, the greater the mass. So if year after year after year these satellites are getting farther and farther and farther apart, that means the ice is growing. If they're getting closer and closer together, the ice is shrinking. Same is true with water on land. If they're getting farther apart, there's an increase in water in land, which I'll talk about in a minute. So that's another tool. And then the last is interferometry, which I won't get into it except to say by tracking the movement of certain features on the surface, we're able to, it's much more complex than I'm making it, but we're able to measure the flow rates. So we can see if glaciers are speeding up or slowing down. And when we put that together, what we're finding is that Antarctica is shrinking some, Greenland is shrinking a lot. Put together, they're shrinking tons, literally, gigatons actually. So if you just look, 3,600 gigatons is about 10 millimeters of sea level rise over this period here. 360 gigatons is a millimeter of sea level rise. So we're starting to see the contributions from Antarctica to rising seas. And again, since my theme here is perspective, understanding what's happening is enabled simply by watching. So in the late 70s, early 1980s, somebody had theorized that, if you remove the floating ice, the glaciers that flow into it will speed up. And this is a mechanism by which sea level can rise rapidly instead of slowly, because glaciers tend to move slowly in today's climate. And in the 90s, that was proven wrong. Theoretically, with models, it just can't happen. And then Mother Nature did something really amazing. In a month, an area about the size of Rhode Island, and for reasons I won't get into, the standard unit of measure for icebergs is small New England states. But what happened was when this ice went away, all of these glaciers that fed it sped up. So once this, what is vulnerable to today's climate, was removed, the resistive forces were removed, and these glaciers sped up. And Mother Nature did a control experiment too. It left some ice there. None of these that fed the ice sped up. So this proof turned out to be wrong. And all it took was a catastrophe in Antarctica to really understand that. But again, when we watch, we understand. This is just a map of the outlet glaciers, the velocities on the Greenland ice sheet. You can see the outlet glaciers. We track their speeds in time, and all of these, which deliver most of the ice from Greenland to the ocean each year, most of the mass losses through those glaciers are speeding up. And this is, we have instruments that measure sea level. Altimetry measures ocean height, and this is just a history back from 1993 of the sea level rise, change in mean sea level. So we're up to about 80 millimeters sea level over the time period. And you can see there's some cold years, ocean thermal expansion plays a part, where sea level went down, and some years when it went up more than others. It's a mixture of temperature and the addition of mass or water to the ice cover. But again, the perspective. So this is the spatial representation of surface height change from that same period, 1993 to 2015. And you can see some areas, especially warm, go up quite a bit with respect to sea level rise. Some areas go down where it's cooler. And in the case of a place like Greenland or Antarctica, the sea level is going up a little bit. You see the yellows are a little above the zero. But the interesting thing is, as we know, as it's losing ice, the gravity of the ice sheet is less, so the extent to which it pulls water towards itself goes down. So it's kind of counterintuitive. As it loses a lot of ice, the sea level in the vicinity actually goes down because the gravity is not pulling it as close to it anymore, but it's ending up in other places. I mentioned we could also measure the gravity of water, and this is a map of the world showing water either stored in soil in rainforests or in aquifers below the ground. This is another reason I think this instrument is fascinating, because you can assess what's happening underground. And if you just look at the United States, this is the drought in California, the depletion of the aquifers. You can see the loss of water. Even though it's happening underground, we can track the replenishment and the loss. This is just a map of drought risk, vegetation health. So I'm going to take you on a little world tour. Vegetation health. Yeah, this one isn't the movie. By looking at the vegetation health, if it's dry and brown, we know that we have a risk of drought. If it's healthy, we have less of a risk of drought. This shows kind of a combination of what I showed you before, but you can watch the seasonal evolution. I don't know why that isn't. Oh, there it is. Let me go back. Watch the seasonal evolution of vegetation on land and phytoplankton in the water. You see, as the springtime comes, the northern hemisphere warms, and as fall greens, and as fall comes, the northern hemisphere vegetation disappears. Simultaneous with that, you can see the ocean color, and this is an overlay of carbon dioxide in the orangish colors and vegetation on land in the green. And just watch. You can see the carbon uptake. Look at the northern hemisphere. There's a lot of CO2. Spring comes, vegetation grows, the carbon goes away. This is the dynamics of our planet in a chemistry, biology interaction with huge implications for the way we live. I'll skip over this. Well, no, I will show you that. So, this is just a map of ocean temperatures on the top, sea surface temperature anomalies, and net primary productivity, the phytoplankton growth on the bottom. And your eye can tell you they're inversely correlated. And when we look at the structure and the other information, we see, okay, as temperature goes up, the ocean stratifies. The nutrients are deep in the ocean. So the more overturning that occurs, the more nutrients there are, the healthier the phytoplankton is. So high temperatures, more stratification, fewer nutrients, and the productivity goes down. This is understanding the pulse of our planet from these space-based observations. I showed you this earlier, or a version of this, Hurricane Camille, 1969. Again, this was back when we first just had cameras that would look at the behavior. This is an animation showing Hurricane Harvey. Okay, you can see it forming, I think it's labeled, yeah. You see, and what you're looking at is precipitation. The redder it is, the more precip. And you'll see it stall over Houston as it hits the Category 4 level. Just kind of sits there a little longer than everywhere else, and then moves on through Louisiana. So we can track the dynamics, we can track the precipitation. This is from 2005, a very, very active hurricane season. Same general idea. We look at the trajectory of Hurricane Wilma and the precipitation as it approaches the panhandle or the coast of Florida. But I'm going to go one step further now. This is temperature data in the Gulf of Mexico. This is still Hurricane Wilma. But you can see it turns blue in the wake of the hurricane. That is energy going into the hurricane, fueling the hurricane. So from this perspective, we're able to understand these systems in ways we otherwise couldn't. You just couldn't do this with buoys and ships. Well, I wouldn't want to be on the ship, but people try. So this is I'm going to change directions for just a little bit. This was when I became chief scientist at NASA, which is a great gig, by the way. If anyone can do the job, please do, because you won't be sorry. The business card alone was worth it. These were the satellites that were in orbit at the time. And then I'm going to black out every one that is past its design life at that time. So these were all living on borrowed time. There was one satellite. The Earth fleet was really in great peril. And when I became chief scientist, I asked Charlie Bolden, the NASA minister, I said, why me? Why not a Mars guy, or an astrophysicist or somebody? Why an Earth scientist? And he said, our biggest challenges are in Earth science. And I heard you can communicate well, so I wanted to talk to you about the job and see if you can help with our Earth science, selling our Earth science to more conservative members of Congress that may not think it's worth the investment. This is what we have now. Again, most of them are still living on borrowed time, but it's a reasonably robust system. And I mentioned, so Charlie wanted me to deal with the controversy around NASA's Earth Science program. This is a letter that was sent to the chairman of the Commerce, Justice, and Science Committee, subcommittee in the Senate, and the chairman of the House Appropriations Committee. You don't have to read it. The key point is right here. Global warming funding presents an opportunity to reduce spending without unduly impacting NASA's core human spaceflight mission. With your help, we can reorient NASA's mission back toward human spaceflight by reducing funding for climate change research and reallocating the funds to the human spaceflight accounts, all while moving overall discretionary funding down. Charlie gave me this letter and said, I would like you to go talk to these people. So I did, but I did my homework. And this is an excerpt from the National Aeronautics and Space Act of 1958, amended in 1985 under President Reagan. And so whenever someone would say, we got to get NASA back to its core mission, it drove me nuts. Because look at number one. And go back to the rocket with the camera on it. Go back to that 60s movie tone news, story. The expansion of human knowledge of Earth and phenomena in the atmosphere and space. That's part of the core mission. There are others. I won't go through them, but that's number one. And so I learned a lot in my time. Oh, and this is just a history of the Earth science budget at NASA as a percentage of NASA's overall budget. So this was under the Clinton years, under the Bush years, it went down quite a bit. It started to come back under the Obama years. I think President Trump's budget request is back down to about here, but NASA wasn't hit as hard as the other agencies in the president's budget request. But I learned a lot about communicating controversial topics to people who didn't want to hear what you had to say, or people you probably didn't want to talk to yourself sometimes. And the basic lesson is it's usually less about the data than the narrative. We all have stories. We all have a way we see the world. And sometimes all the data in the world is just not going to convince you because you have your narrative. And in some cases, that narrative is Understanding climate, if we acknowledge climate change, it leads to regulations, that's bad for business, therefore we have to not acknowledge it. Or sometimes it's, we're going to hell in a handbasket and we've got to spend all this money on this climate change research. You know, as Mark used to say to me, there's plenty of shrill to go around. So, one thing I took away, and the reason I'm doing this is because we all talk about controversial topics to different audiences. Know your audience. If I learned nothing in my time in Washington, D.C., it's this. If I learned anything in my time in Washington, D.C., I did learn nothing in my time. There are people who are data-driven and there are people who are ideological. Know who you're speaking to. Because the conversation is very different if you take one tack versus another, or you address one audience versus another. I love this. Attitude matters. You know, I made the most headway, and very often I would get from the most conservative of members of Congress, "You're not what I thought you'd be. You know, I expected you to come in here and club me over the head about why I'm wrong and you're right, and I have to do, what you want." But when you go in and say, look, there's something we both care about. We both care about the health of this world, this country, financially, humanitarian, otherwise. And that, starting the conversation that way with that kind of attitude, and we can talk about the value of knowing what tomorrow will bring, really got me a lot farther than data. So my basic rules, this is what I learned in Washington, D.C., and then I'll wrap it up very quickly. Understand the context. That first sub-bullet is critical. They're not as dumb as you want them to be. There's a part of us all when we argue that just wants the other person to be stupid because that just makes it easy. If you take the time to understand what someone believes and why, you can have a much more constructive conversation around it. Frame your views in ways that resonate. This is what I usually tell my fellow scientists. It's very easy for us to be well, if you knew what I knew, you'd just see things my way and understand. That doesn't work. That just doesn't work. But again, you go to what someone cares about, you have a much more constructive and productive conversation. Don't tell people what they should think. There's just a part of us that says, oh, you should see it this way. Generally, beliefs and positions are rooted in values, and you should never expect your values to change another person's beliefs. That is one of the biggest problems I saw in Washington as well. Part of the condescension is, I weight this much, you weight this that much, and you're wrong because the weight should be this much. You just have to accept people are going to be different, and it's rooted in their values. Don't be outcome-centric. A lot of times we're just targeted at getting what we want. Have the conversation. You may learn something. I learned a lot. So in the context of Earth observations from space and the power of perspectives, the way I frame these discussions is in this way. In fact, I did a little bit of work with the White House transition team. I wrote a short white paper for them called 10 non-climate change reasons why investing in earth science is a good idea. These are, I don't know if there are 10 there, but there are most of them. So, perspective, whether it's perspective on our planet from space, or whether it's perspective in a conversation of how and why a person feels like he or she does, they're both of tremendous value if we use them correctly, if we use them well. And so that's sort of that is my message. So thank you, and I'm happy to take any questions. Sorry, I went a little longer than I intended, but
You have a couple of questions?
you can grab me while you're drinking a beer too, if you want. Nothing. It's Miller time. Anything?
No, it's a joke, Wally. Can you get pregnant standing up?
You can't. I did learn something in that class. Anything else? Disappearing ice cover. Time in Washington. I will tell you one thing if nobody's got a question. Everybody should go to Washington, D.C. and everybody should do it with an exit strategy. It's too easy to get stuck there. My wife, it was going to be a 2-year postdoc adventure at NASA, and then I got hired as a civil servant, and then I got better opportunities there, and every couple of years she'd come in and say, we were supposed to get on with our lives by now. When's that going to happen? So I finally made good when I brought her back to Boulder, and then took her back to DC for 2 years. Anything? Yeah.
Yeah, do you have any examples of how you were able to swing a person to a different point of view based on those 10 things that you listed?
You know, yes, inside their office, but when it came time to stand on the floor, particularly in the House of Representatives, because districts are so gerrymandered that positions aren't going to change. You know, they would posture for their constituencies. But I'll tell you this, congressional staff are generally very, very smart. And whatever you're hearing from a member of Congress publicly, it's been my experience the staff, and sometimes the member, really want to know, really want to understand. And admittedly, it's so often so they could frame an argument in the way they want to. But I felt like I at least elevated the conversation and that it was built into the thinking. It was interesting, I got a call a couple days ago asking me to testify on geoengineering, putting a bunch of crap into the atmosphere to keep the planet cool. This was from Lamar Smith's staffer, so chair of the House Science Committee. And I was fascinated because he was asking, very smart, and at 29, these guys are just, they're incredible. But he was saying, basically, climate's changing too fast for regulations to work, so we wonder if we should be studying putting crap into the atmosphere. I'm phrasing it a little differently. And I found that remarkable. Like, once cast in the context of should we invest in geoengineering research, climate change was real. Cast in the context of should we regulate CO2 emissions, climate change was a hoax from the same person. So I have to believe, well, I can't point to, oh, this legislation came because I had that conversation. You know, I don't have that kind of influence in Washington. But I have to believe that people think about what's said and build it into their actions.
Well, I have a serious question.
Your other one wasn't serious?
Sort of. I'm still curious. No. I'm curious about the use of satellite imagery to track human rights abuses. That is, by human rights groups using satellite imagery, let's say, look at the destruction of villages in Darfur and other kinds of high-resolution imagery that shows very clear. So, I don't understand. Can the government satellites be targeted and directed to those places, or are they in fixed?
The government satellites can, but there are some pretty strict laws where you get down below 10-meter resolution, it's the domain of the commercial industry. So what happens is units like, entities like USAID and others will just will pay to private companies to task satellites to make those observations. Now, on large-scale destruction, a lot of the NASA satellites, they're just operating constantly because they're not such high resolution, they don't need to be so duty cycled. Well, the Landsat does, but generally, if there is an issue that the State Department is concerned about and NASA can help, or that the military is concerned about and NASA can help, NASA will release those data. I mean, they're publicly available anyways, but will orient the satellites or make the observations in any way that can help. But the kinds of stuff you're talking about are largely supported by the commercial entities, and it's much more of a purchase for imagery sort of thing. Or, quite frankly, you know, humanitarian crises are often coupled to terrorist threats and things that interest our military. So the military has assets that I'm assuming they work closely with the State Department on in those kinds of things as well. Does that make sense?
Yeah.
Okay. Anything else? Yeah.
Why didn't you try to become an astronaut?
I did, And I failed. I wrote my letter, and I typed it, because that's what you did then, and I wrote, I want to be an astronaut in capital letters, and I got a very nice, we get 20,000 applicants, and you're not going to be one of the ones that move forward, which is fine. I will say, because Chief Scientist, again, was a good gig. And the astronauts, this is interesting, the astronauts have to take training, they have a week-long course on Earth science. And so I was asked to teach that. So I went to Johnson Space Center, and I sat with the astronaut class of 8 people, and I saw why I wasn't selected. I mean, these people were brilliant. And I tell you, imagine you give a talk, right, to a science audience, you cast it one way, to a general audience, you cast it another, but to a brilliant general audience, that's a hard place to find when you're giving a talk. But they were just remarkable people. One of my friends, he ended up heading the education division at NASA, was a professional football player and then an astronaut. And when Charlie used to introduce him, he'd say, he's realized 2 childhood dreams. And I'm like, oh, I didn't even realize one. I saw one hand. Is time for one more question, or?
Sure.
Okay, yeah, Tim.
So this is kind of a philosophical question, but
love philosophy.
I mean, so on the one hand, you kind of give us a picture of increasing ability of kind of instrumentation that is able to give us a clear picture of what's happening and what may be happening.
Mm-hmm.
And on the other hand, and the story of the Larsen Ice Shelf is really interesting in this context, because on the other hand, you've got a supercharged system that seems increasingly difficult to predict.
Yeah.
And so can you reflect on that a little bit in terms of, are we in a situation where there's less and less that we know about what's going to happen in terms of being able to predict catastrophic events, for example, and how does that kind of, how do we work with that, given our seemingly ability to kind of know everything that's happening?
Well, there's the saying, the more you know, the more you realize what you don't know. And part of what you're seeing is a manifestation of that. But I think the direction is progressively improving. I feel like take hurricane trajectories. Now, this is more a NOAA issue than NASA. But the fact that we knew where Harvey was going to hit and where Irma was going to hit allowed much more controlled evacuations, better timed evacuations, people caught less off guard. So while the system may seem increasingly intractable because we're learning how complex it is, the reality is I think we're understanding processes a lot better. And I think we have the means to understand them in ways that will return tremendous value if we have the wherewithal to invest in them, but I recognize that competes with other resources. So I think if you just look at the trajectory of our understanding and what we've been able to do with it, it's been pretty positive, pretty clear. So the system is chaotic and hard to predict, but we have done much better than we used to, and we can do much better in the future. Does that make sense?
Yeah,
Are we converging?
Well, it seems like it's getting harder to predict as our ability to predict it also gets better. Is that fair to say?
I don't know that that's true. I think it seems that way, and we're putting more energy into the system, and that lends itself to instabilities a little more. But no, I don't think it's outpacing us. I think we're gaining on it. And 100 years from now, we'll know it all.
On that note, please join me in thanking Waleed.
Thank you.